Hi, this is the third lecture of our lectures on Einstein-Maxwell manifolds. So yesterday we obtained the so-called Reinig algebraic conditions for a geometric solution of its geometric conditions for Einstein-Maxwell equations. Hopefully we'll apply this to an example, but before that we need to obtain some more results. So we need to start with duality rotation. Let F be a complex electromagnetic vector. Be a complex electromagnetic vector defined by F equals E plus IB. These are vectors. And we can consider that this complex electromagnetic vector is a result from a complex rotation of another vector. Consider that F vector is a result of a complex rotation of vector capital F, which is E plus I capital B. So when we say a complex rotation, we mean this type of rotation, and such that E plus IB by using Euler identity sine alpha plus B cosine alpha. So we get cosine alpha plus B sine alpha, and small b becomes and we can choose the condition here where E is perpendicular to B. Then by multiplication, by dot product, we got, of course, these are vectors. Plus E dot B cosine square alpha minus sine square alpha. So since they are perpendicular, it has to be 0. And this can be further simplified. By the trigonometric relation. And from here, we can find the tangent to alpha. Is 2E dot B E square minus B square. And previously we have given the relation with electromagnetic field strength tensor F mu nu and electrical field E mu and B mu is dual U nu. And U is another velocity vector. So the complex EM vector F can be also shown as a result of a contraction of 4 velocity. This U, it's in 4 dimensions, so we say 4 velocity U nu with a self-dual bivector. So what we mean is F can be shown to be F nu F mu nu U nu plus I F tilde, which is the self-dual bivector, and that is equal to E mu plus I B mu. And here E can be written as again contraction. It's already seen from this line, F mu nu, U nu, and B becomes B nu, F mu nu tilde U nu. Then it follows from equation numbers 16, 17. From these above definitions, and this rotation, this one, we have the transformation or duality rotation. That we have let's say transformation or duality rotation. And that is F mu nu tilde is equal to F mu nu capital minus I alpha. From yesterday there was this question about this complexified strength tensor. So now we are using it in this duality rotation, or F mu nu is equal to F mu nu cosine alpha sine alpha and tilde minus F mu nu sine alpha cosine alpha. And 24. And this is valid at each point of space-time. On, let's say, manifold. And if we evaluate the contraction, it's just straightforward calculation. Of course, we said contraction, so we need to be careful about places of indices. And also here. Sine alpha, cosine alpha, and the cross terms cosine square alpha minus sine square alpha. And again, by using the trigonometric identity, becomes minus f mu nu f mu nu sine 2 alpha here we used f mu nu contracted with itself is minus f tilde mu nu tilde mu nu. By using the definition of dual tensor, you can easily check that. Then when you insert this identity here, you have two of it. F mu f tilde mu cosine 2 alpha. And we also give this contraction in terms of B and E before. We have, let's mention again here. It was given as minus 2 parenthesis b square or even the other way, e square minus b square. And f mu nu f tilde mu nu was minus 2 e dot b. And if we use in this construction, sorry, we have minus here. Then this becomes 2 e square minus b square sine 2 alpha minus 4 e dot b cosine 2 alpha. Then we can obtain this tangent 2 alpha in 20, equation 20. We obtain if we impose the following condition. Which is f mu nu, f tilde mu nu, this contraction has to be 0, and this has a let's call this 25, and this is called extremal field. If we satisfy this contraction, then if we consider an angle alpha in a duality rotation such that 20 and 25 are satisfied, we have a coordinate system where small e is perpendicular to b. That was our assumption, and it is satisfied on under these conditions. such that equation 20 and 25 are satisfied, then we have a coordinate system where E is perpendicular to B. And we also have inverse transformation from f mu, small f mu nu's. We can obtain capital F mu nu, the regular usual field strength that we use in Maxwell equations. F mu nu is equal to small f mu nu cosine alpha minus f mu nu sine alpha, and this one and from these we can have some identities. These are again straightforward. For external field condition, from these transformations with external field condition in 25, we obtain the following contractions. Cosine 2 alpha and the tilde contraction with the normal tensor. And this gives us sine 2 alpha. Then if we take the square, if we add up the squares of these terms, plus this term square, it's obvious that this will be this contraction squared. And this transformation from small f mu to field strength, or standard field strength capital F mu, and which is in accordance with this angle rotation in equation 17. These are discussed by Reinig, and it was called duality rotation by Misner and Wheeler. And they call the field F mu, this small F mu, with the properties of this extremal field. When you satisfy this, they called it extremal field. And the actual electromagnetic field F mu at a point can be obtained from the extremal field by a duality rotation through the angle alpha. And here alpha is called the complexion of electromagnetic field at the point. Let's mention that, because in literature you will see this. The actual EM field F mu at a point can be obtained from the external field by a duality rotation through the angle alpha, where alpha is called the complexion of EM field at the point. Okay, now we want to see how Ricci curvature tensor transforms under duality rotation. Ricci curvature tensor under duality rotations So let's again recall Einstein-Maxwell equation for we call this electrovac equations. R mu is equal to kappa over 2 F mu rho F nu rho plus dual tensor f with tilde nu rho tilde nu rho. And we also show that this can be written by this complex field strength, complexified. With this, we show this by this curly f, and this is the complex conjugate, and that is invariant under under duality rotation of electromagnetic field. EM field according to this duality rotation which we have given in 23. In accordance with 23, where this complexified field strength rotates with angle alpha. And we also have given this inverse transformation of the actual field strength in terms of this transformed f minus small f. And let's see, by using equation 26, inverse transformation we obtain actually we are going to need these parts in Einstein-Maxwell equation that we have just written, and for that let's say f nu rho cosine square alpha f tilde mu nu and the tilde, new row, sine square alpha minus new row plus f new, sorry, a little room here. Okay. We should keep track of indices in the correct position. Okay, yes. Sine alpha, cosine alpha. Actually, we are just using this equation 26 and taking this contraction in one index. And for the tilde, the dual tensor, we do the similar calculation. Let's see, I think it's better to copy this. Okay, just this is going to be sine square alpha and this one cosine square alpha and this one is same. Okay, and if we add this together, addition of two above equations results in the following. F new row plus the tilde ones, F new tilde F new row, and that becomes F new row plus just a second, we just need a plus sign here. Okay, now we are good. Then here we have, sorry, F tilde new, again F tilde new row. And you can easily, when we check this, and compare with these Einstein-Maxwell electrovacuum equations, you just need to lower new index, and this is easily done by the metric. I mean, we're going to lower the new, so we just need to apply G new, let's say lambda. If we apply this one, then okay. Let's say rho lambda. The previous one was the right one. Lambda. Actually, you are going to obtain here. Let's see. F lambda rho rows are contract. Okay, new will stay there. Okay. It's just confusion with the indexes. So here row becomes new. So we just need to lower the index row here and then shuffle the indices between row and new. I mean, row lambda. Yes, because this has to be in the contraction case with this one. So then we will obtain here F new lambda. Yes, that's the right one. And then since new is dummy index here and also row is dummy index here, just set new to row and lambda to new. That's actually an easy thing to do. So if we use this in above equation, we have that Einstein-Maxwell system of simultaneous equations. Maxwell system of simultaneous equations. Source free. EM field case is RMU is equal to, let's just copy that one. And by our new result we just obtained above, 2 small f new row plus f new row. So that it means it is invariant under duality rotation of electromagnetic field. Okay. Then we want to apply these results to real space-time, but we just need one more formalism. It is Newman-Penrose formalism, spinor. Let's say the Newman. Actually, I won't give too much detail in here, but we are going to take some parts and use it in our calculations. Penrose formalism. Here we are going to use the spin coefficients. And this they have this so-called null tetrad formalism, and the null tetrad formalism due to Newman and Penrose has proved very useful in the construction of exact solutions. And let's just briefly say, using the complex null tetrad, M bar, L and K, and recalling the covariant derivative definition. BEA was given in terms of Christoffel symbols, like this. Then we define the so-called spin coefficients. Spin coefficients, which are 12 independent complex linear combinations of the connection coefficients. Spin coefficients There are 12 independent complex linear combinations of the connection coefficients. We mean these Christoffel symbols. Combinations of the connection coefficients, and we are going to give them explicitly. The spin coefficients are in tensor notation kappa. So these are all definitions. We will have, let's see, 1, 4, yes, we have 12 of them. Gamma 1, 4, 4, and in terms of these tetrad vectors, A, D, K, A, we are going to define this D capital D minus rho one for 2, and that is A delta bar Ka sigma 1 for 1 Ma delta Ka and tau 1 for 3 Ma delta Ka. Okay, Ma bar delta La and nu are 2, 3, 2 delta bar La pi let's see, maybe I can just copy from. We are going to use these definitions in our calculations. Just to spare some time, maybe it's better to put this here. Maybe we already have put the other ones. Okay, and let's also give this capital D, delta, capital delta, and others. So these are the definitions that we are going to use in our calculations. So we want to, let's see, example. Now that we have all the necessary tools, consider the homogeneous pure radiation metric given by minus 2 e to the 2wx du tensor du plus du tensor dv, dv tensor du, dx and dy tensor dy. So we have such a simple metric. Actually, it's shown simple, but we'll see that this is satisfying the Einstein-Maxwell equation. And also we are going to see we need to obtain the field strength, which will satisfy our Einstein-Maxwell equations. But I think we can stop at this point, and we will apply this in the next lecture. What we are going to do is we need to obtain the Ricci tensor. We know how to obtain for a given metric. Maybe I can give it here. The Ricci tensor R of this metric is obtained so the component is this coefficient, and since we are using the tensor, it is this. So we know that R mu in the tensor so that means other than du cross du, let's say it corresponds to first R11, so this is R11 dx1 tensor dx1. The other coefficients of the tensor become 0. That is just straightforward calculation. But then we are going to choose a null vector field K in this complex null tetrad. Then we are going to write an adapted null tetrad. Then by using Newman-Penrose spin coefficients, we are going to obtain some PDEs and solve these PDEs and obtain field strength. Then show this solves Einstein-Maxwell equation. Okay, I think we'll continue next lecture.